All right, everybody, welcome back. Today we're tackling the mean value theorem. Not the nice value theorem, it's the mean value theorem. Let's get started. With that, we've covered a lot in this playlist of videos so far. Differentiability is going to be very important for this one. And then we'll move into vertical, horizontal tangent lines, and equations of tangent lines. With that, 4 keys to success for the mean value theorem. They are: know the language of the mean value theorem, see the mean value theorem graphically, apply the mean value theorem to a function given algebraically, and then also be able to apply the mean value theorem to a function given in a table. If you can see and do these 4 things, you'll be good to go, the mean value theorem. So it's important to know the language of the mean value theorem. The first part of this is called the criteria. And if this criteria is satisfied, then the second part is guaranteed. I like to call the second part the conclusion. So you have the criteria and the conclusion. The criteria has 2 pieces. First, the function must be continuous over a closed interval AB. Graphically, that means you could draw without picking up your pencil, or that the limit as x approaches every value between those values equals the value of the function between those values. So, and then the second part is must be differentiable over the open interval as well. Meaning it's a smooth curve, no corners, cusps, or vertical tangents. Then, if those 2 things are true, then there's a number C such that A less than C less than B. That's just saying C is between A and B, where the derivative at C equals the average rate of change, f of B minus f of A over B minus A. It's a lot to take in. Take a moment to play this back if you need it broken down, or just look at it to make sure you got it down. Check for understandings coming up on the next page. Can you see or say the mean value theorem yet? Take a moment to see if you can say it, or at least get close. And here it is. If the function f of x is continuous over the closed interval, AB, and differentiable over the open interval, AB, then there is a number C such that A is less than C less than B, where f prime of C is equal to f of B minus f of A all over B minus A. So with that, let's see this in action graphically. Here I'm given a function x squared, and I'm looking at the interval -2 to 2. Simple parabola. First 2 things I need to ask myself if I'm going to use the mean value theorem are, is it continuous, is it differentiable? Let's focus on the first part. Between -2 and 2, I see the graph can be drawn without picking up my pencil. So it's continuous. How about differentiable? If I look between -2 and 2, it's a smooth curve, no corners, cusps. I could draw a tangent line anywhere there. Also makes it differentiable. So given that that's true, then there's some value C where f prime of C equals f of 2 minus f of -2 over 2 minus -2. That comes directly from those values on the right side, come directly from the interval given at the top of your screen. Given that, we see on the graph that there is a point at x equals 0 where the tangent line is parallel to that secant line that we found the slope of, or the average rate of change. So the value of C here would be equal to 1, but equal to 0, which then also matches the average rate of change, which was 0. We'll see a few more examples with a few different cases. With that, quick check for understanding. What 2 properties must be true about a function for the mean value theorem to apply? 2 are continuous and differentiable. Continuous over the closed interval, differentiable over the open interval. With that, let's take this to an algebraic context this time. Take a moment to copy that down if you're following along at home, and I'm going to take you to the dot cam so you can see my thinking more clearly. That's example 2. Here's example 1. Let's read it together. Consider the function f of x equals x squared minus 3x. Does the mean value theorem apply over the interval 0 to 2? If so, find the value of C that is guaranteed by the mean value theorem. Okay, a lot to do here. Does the mean value theorem apply over the interval? Question mark. And if so, find the value C that is guaranteed. So that's what we're trying to find next. Let's go and do one thing at a time. Let's do this first, and then this part second. So does the mean value theorem apply? I need to think back to that criteria. Does the mean value theorem apply? I think so, but let's make sure we're really clear about that. My graph might look something like this, and I'm concerned about x equals 0 to x equals 2. Can I draw that without picking up my pencil? Yes, I can. So that makes this function continuous. And then, can I draw a tangent line everywhere between 0 and 2? I can. So that makes the function differentiable. This tells me that mean value theorem applies. It's essentially like, are these two things true? Yes? Great, you can use this theorem. So now the next part is where it gets a little bit tricky. So I'm gonna really break it down. Once I know the mean value theorem applies, I know this equation is going to be true for some value C. And that value C is gonna be between that interval 0 to 2. So let's find out what that interval is first. I'm gonna keep f prime of C here for now. B is gonna be 2, and A is gonna be 0. That's my left and right endpoints, 2 minus 0. I'm gonna do some quick mental math here. F prime of C equals f of 2 would be 2 squared minus 3 times 2. That's 4 minus 6. That gives me, 4 minus 6, that's negative 2. Minus f of 0 would just be 0. Over 2 minus 0, that gives me negative 1. Now be careful here. We have not found C. We just know the derivative at C equals negative 1. So we got to go one more step here where we're going to find out what C is. So f prime of C equals negative 1. So what we need to do next is take the derivative and substitute C. The derivative is going to be 2x minus 3. So my f prime of C is going to be 2c minus 3 equals negative 1. Now we're almost there. I'm going to add 3 to both sides. I get 2c equals 2, c equals 1. So what we're saying is that at c equals 1, the derivative is equal to that average rate of change, which was negative 1. Let's take it back to the PowerPoint to see what that looks like graphically. If you need to replay it, the beauty of video is you can pause and replay anything. So feel free to rewind if needed. All right, here we go. So we did some work here over in gray. Let's think about this graphically now. Here's the same curve on the right, x squared minus 3x. And what we found first was that the average rate of change from 0 to 2 was negative 1. That's represented by the green line that you see intersecting the parabola on the right. Then what we did is we set f prime of c equal to negative 1, and we found that c equaled 1. You can see on the graph, the blue line at x equals 1 is tangent to the curve, and it's parallel to the secant line, which has a slope of negative 1. So this is connects back with the graphical representation we saw earlier and backs up that our answer is correct. With that, now let's take it to an example where we're given a table. This is very popular on FRQs, particularly parts C and D, which tend to be a little bit tougher on those AP exams. I'm gonna take it back to the doc cam where the same thing written. All right, here we go. Here is example 2. Let's tackle this last one and we'll be done with the mean value theorem. Consider the twice differentiable function f of x over the interval 0 to 10. Okay, this is from 0 to 10. Twice differentiable, let's think about what that means. Differentiable would just mean the derivative exists. Twice differentiable is another way of saying the second derivative exists and the first derivative exists. So that's just some new lingo you might see pop up later. Select values you're given in the table below. Great, I have a table. Based off the information, is there a value c on the interval 3, 7 such that f prime of c equals 3? Justify your reasoning. Well, I know the table has f of x values, but this is talking about the derivative. So I'm gonna need something related to derivatives. I also know the function is twice differentiable, so it's also differentiable. And I know if it's differentiable, it's also continuous. So I know two things about this curve. It is continuous on 0, 10, and it is differentiable on 0, 10 as well. And so can I apply the mean value theorem? Well, it's continuous and differentiable on 0 to 10. 3, 7 is within that interval, so it must also work on that interval. So then we can say MVT applies. Great. Now we're going to use similar thinking from before, even though we don't have a function algebraically. So here we go. I just need to show that there's a value c that exists. I just need to use the theorem to prove that. So let's see let's start with our equation from before. F prime of C equals F of 7 minus F of 3 over 7 minus 3. F of 7 is 20. F of 3 is 8. 7 minus 3, this will be 12 over 4, which equals 3. Aha, that's a good sign. It's a very good sign. I found that the average rate of change was 3. So I see F prime of C, based off the mean value theorem, must equal 3 at some point. That matches up nicely with my prompt here. So I've kind of found the code that answers this question. So altogether, to get these justification points, here's how you can put that together. The function f of x is continuous and differentiable over 3, 7. Therefore, the mean value theorem guarantees there exists a value C such that f prime of C equals f of 7 minus f of 3 over 7 minus 3, which equals 3. There we go. If you're asked to justify here, you do need a full expression like this, putting all your thinking into just one synthesized statement. So if you need to replay into that, beauty of video is you can go back and replay it, slow it down, speed it up, whatever you got to do. Take it back to the PowerPoint to close this out. We just tackled this example. What's the name of our keys to success so you know what you need to leave with? You need to know the language of the mean value theorem. Continuous on the closed interval, differentiable in the open interval. Therefore, there must exist a value C such that f prime of C equals the average rate of change over that interval. Next, make sure you can see the mean value theorem graphically. Make sure you can apply it algebraically. That was example 1. And make sure you can apply it in the context of a table. That closes out this video on the mean value theorem. And we'll take you to horizontal vertical tangents next. Hope this helped you level up in AP Calculus or College Calculus, whatever you're studying. And please leave some feedback below if there's any ways we can make these videos better. Thank you.